And now we have Roman Valk from Tatseo. Please.
Spoiler, I guess. How can I go back there?
With the button.
Yeah. So you now see my slides already? Good. So hi everyone, my talk is titled Scaling Private Iris Code Uniqueness Checks to Millions of Users, and this is joint work with Remco Blömen, Brian Gillespie, Daniel Kales, Philipp Sippel, and me. So this talk is about building a biometric-based data application server in MPC, and this essentially means that we want to build a service where people can sign up using biometric data, but exactly once. There are two motivating use cases for such a service, and one is World ID. This is the one that we have been working on, and what they want to build is so-called proof of humanity, which is built to combat the rise of bot accounts on the internet. And they achieve this proof of humanity by using biometric data and using a data application service here that people can only sign up once. A second use case, this was proposed by a paper called Janus that was published last year at SMP, is a human aid distribution by the Red Cross. And the motivation behind using a data application service is that usually these services have scarce resources and they want to reach as many people as possible. So people should only be able to sign up once. And the reason why they use biometric data and not something like passports is that most people qualifying for human aid don't have access to a government-issued passport or something like that. So how does a data application service look like? So you usually have some device in the World ID infrastructure. This is called the orb that takes a picture of your iris, derives something called an iris code, and sends it to a server who checks if the iris code was already used for registration. And it does that by holding a database of all iris codes that have been registered so far. And here should the alarm bells of all privacy-sensitive people should ring here, because this is a huge privacy issue if a company stores biometric data of these users. So a huge privacy problem. Also, it allows a lot of potential misuse opportunities. For example, they could try reconstructing ethnic information from the iris codes and censor some specific ethnicities, or they could also say, I don't want to process iris codes from specific countries, so a lot of misuse potential. And besides all of that, governments usually also don't like companies who store biometric data of the users. So not an ideal solution, but there is definitely an ideal solution, and that is using MPC for this service. So how would that look like? So instead of having one party holding the database of the iris codes, we split it using secret sharing. So we have multiple parties now, and they hold secret shares of the database. And as long as they do not collude, no one learns anything about the iris codes they actually stored in the database. Also, the orb now, instead of sending out the iris codes in plain, it sends them out in a secret shared fashion, and we use MPC to check whether this new iris code is actually already present in the database. So it sounds very nice, but there's obviously a huge problem there, and that is performance. So I was previously mentioning this Janus paper last year at SMP, and they had pretty much the same protocol here, implemented it, and their MPC-based solution only achieved a throughput about 2,000 iris code comparisons per minute. And when we look at the database size of World ID, where currently 11 million people are registered, we can see that it's definitely too slow for a practical deployment. So we have to come up with some different solution here. So let's talk first about the actual protocol to compare to iris codes. And so what the orb produces is the iris code here C is essentially just a large bit vector, and it also produces some mask, which is another bit vector, which is used to hide some faulty bits, for example, when some eyelashes were in the picture, so some bits are not valid in the comparison. And what we then use for a comparison is the so-called fractional Hamming distance. So essentially, you first have to combine the mask to remove all the bits from both iris codes that you want to compare. And then what you do is here you basically just XOR both iris codes, remove the faulty bits by using the end operation with the mask vector, count how many bits are set, and divide them by how many bits are set in the mask. And if this, the result of this division is smaller than a predefined threshold, then it's actually a match. If it's larger, then the irises do not match. So this sounds like a very simple protocol, but when we want to translate this to an MPC solution, then you will see that it is actually not that easy to make it efficient. And there are multiple reasons for that. First, it's actually a mixed protocol, so ideally you want to do the XOR and AND operations in a bitwise sharing, and then you have to sum up the how many bits are set. You usually want to do that in when computing over a larger ring, and then you have to go back to a bitwise sharing to actually perform this comparison here. The second issue is that the data sizes involved are very large. So in World ID, the iris codes have a size of 12,800 bits, and the database size, as I mentioned before, is currently at 11 million iris codes, and it is also growing. So alone here, the database is hundreds of gigabits of data here. And that, when we process the iris code similarity check on the whole database, this leads to a lot of communication overhead. And this is also the issue that is limiting the performance of this Janus paper. They were using garbled circuits, and the communication just blows up too much, and that's why they only have this throughput of 2,000 iris code comparisons per minute. So we need to find a way to reduce this communication here. And when we look at the protocol, that the Hamming distance is actually the part where we have the biggest communication overhead. And what we realized when we were first looking at this problem is that when we rewrite the Hamming distance to this expression here on the slides, you can see when we would use secret sharing, there is two sums and a dot product, and everything is linear except the dot product. So the only part where communication is induced is in these dot products here. And as MPC researchers know, is that when we use honest majority MPC protocols like Shamir secret sharing or replicated sharing as used in EBI3, then the dot products actually require only to communicate the one ring element. So just by going from garbled circuits to honest majority MPC protocols, we can remove a whole bunch of the communication overhead involved in this protocol. So this is the first thing that we're doing. What is left is then the threshold comparison check, and here we are basically doing what is standard in the literature. So we are rewriting the comparison to a subtraction, and if this subtraction does not overflow, then we can use just an MSB most significant bit extraction here to get the result of the comparison. And in replicated secret sharing protocols, there's a fairly efficient technique that we can use here. So going into a little bit of more details, so this is the most technical slide of my talk, so don't worry, after that it becomes more easy to grasp. So what we ended up doing was using Shamir secret sharing over this weird ring here for the dot product. And the reason for that is that we, on one hand, want to use Shamir secret sharing for the dot product because it is, has less overhead on the CPU compared to replicated secret sharing. But on the other hand, we would love to have the ring set to the power of 16 for the MSB extraction in the second part of the protocol instead of the working over prime fields, because this makes this part of the protocol more efficient. So we ended up using this weird ring. But in the implementation itself, we don't really have to deal with weird polynomial arithmetic, because when we choose the reduction polynomial of this Galois ring, you can see that the resulting constant term is actually the dot product of the input polynomials. And since we also want the result to have to be in arithmetic secret sharing, we can use, can I do that? Yes. We can multiply the Lagrange coefficient here that is used to translate from Shamir secret sharing to additive secret sharing. We can multiply that onto the query beforehand, and then the result of this multiplication, we just take the constant term here, and this is the resulting dot product in additive secret sharing. So in the end, when we consider all of this, we only have to consider multiplying the Lagrange coefficient onto the query iris code, and the rest is as if we would not do Shamir secret sharing or Galois over Galois field at all. So this is a very nice result. So after this dot product, we essentially have an additive secret sharing in the ring set to the power of 16. To translate this to a replicated secret sharing like AB3, this is fairly straightforward. We just have to send the shares to one of the other parties, and then we can continue with the MSB extraction. And here, so since we want to compare against the threshold, which is usually some real number, we approximate it by some fraction here, and then we just evaluate this term here and extract the MSB. And that is essentially the protocol that we implemented. So in the paper, we have a lot of more details. There's a link to the paper on my last slide. So if you're interested, check this out. For now, this is just all of the protocol. So we finished a prototype of this protocol already a year ago, and here are some benchmarks for it. So here, this is comparing an iris code against a database of 100,000 iris codes, single-threaded benchmark in a LAN setting. And you could see that for this benchmark, it took, in the semi-honest setting, 145 milliseconds. That is a throughput of around 690,000 iris code comparisons per second. So by going from garbled circuits to honest majority, we can really boost the throughput here. What you can also see here, the first phase is very, first phase, dot product is very compute heavy with little communication, and the second phase is actually very network heavy but little of computation. So how can we increase the performance of this protocol? So since we have the first phase essentially just computing dot products, we were considering using GPU acceleration for that. So this worked out very nicely, but what about the second part of the protocol, where we have very little CPU computation interleaved by a lot of network rounds with a lot of network? The answer to that is this is also very GPU friendly, because when we're using something that's called NVIDIA NCCL, we can actually let the graphic cards directly access the network interface. So what we ended up doing was implementing the whole protocol on GPUs. The GPUs were directly communicating with the network interface, and we never had to do any transfer between the GPU memory to the normal memory, which usually incurs a lot of overhead. So in the end, after we implemented this protocol, we essentially had multiple servers which were running GPUs, and these GPUs were doing MPC with each other. So we also have benchmarks for this here, and the setup was we had it's a very expensive setup, 3 servers which have each access to 8 H100 GPUs, so essentially the best you can get out there, and they were also connected with a very fast network connection of theoretically up to 3.2 terabits per second. In practice, we don't get this number, but something close to it. And here we did a benchmark for a database size of 4.2 million iris codes and had a more real world setup here. So we wanted to match a batch of 32 people. And for security, what you have to do usually is you have to match both eyes of the person, and to reduce the error probability, you also have to match rotations per each eye of the person. So 31 rotations. So in total, per person, it's 62 iris codes, and for 32 people, it's matching 1,984 iris codes to the database of 4.2 million codes here. And you can see with this very nice setup here, we get only a runtime of 1.9 seconds here, and that is a throughput of 4.3 billion iris code comparisons here. So with a nice setup, we can increase throughput even further. So this GPU protocol on this nice hardware is actually deployed nowadays in the World ID infrastructure. If you are interested in the source code, I have linked it here on the slides. It's on GitHub, so you can check it out. So as I said, it's currently deployed in World ID, so whenever you scan your iris and we want to register for World ID, actually the MPC code here that we implemented is used. So and since this service was also deployed before we did the MPC solution, it's worth to mention that the World Foundation has deleted their pre-MPC database. So how does deployment actually look like? So World ID is not hosting any of the MPC computing nodes, so they partnered up with some universities and a research company, and each of these partners takes care of hosting one node on their own. So we have Berkeley, University of Zurich, and Friedrich Alexander Universität, and the company is Nethermind. So World ID does not have access to any of the databases with the secret shares. So there's one guy making photo, the iris code, I guess. Great. So I want to talk a little bit about our road to deployment, because I come from research and we usually just write prototypes, and to give you a sense on how long it actually took to get this protocol deployment ready. So in the beginning there were essentially 4 researchers doing work on the protocol and the implementation, and once we decided to actually go forward with deployment, it took another 7 months, so twice as much time, and a lot more people from DevOps to actually get the protocol production ready. So the reason was, one hand, we wanted to increase performance, so GPU acceleration was part of this process. Then we wanted to make sure that we use all of this fast network environment that I was mentioning before, this 3.2 terabits per second. So we had to do batching of requests, so checking multiple persons at once, and we also wanted to increase parallelism as much as possible. For example, we have that 2 different phases in the protocol, the dot products and the threshold comparison. The one is compute heavy, the other network heavy. So we do the dot products of one batch in parallel to the threshold computation of the other batch, and this also requires us to make sure that there are no duplicates of iris codes between these batches. So additional checks there. So a lot of performance improvement had to be done there, but also production readiness. Usually when you're a researcher, we write our MPC prototype. If it crashes, well, it crashed. Let's do another benchmark. So this is not something we want to have in production. So we had to build a robust system where the iris, the orbs can actually push new secret shares to some queue, and the servers can actually process this queue. Also the teams, World ID want to know what's going on, so they want to have metrics on how many iris codes are in a database, how many get included, how long is runtime currently for a batch, etc., etc. So tracing and metrics has to be added. And the thing that is not to underestimate in a very optimized parallel system with MPC is you have to keep the databases of all the parties in sync. Whenever you get out of sync, you essentially have garbage data in the database, and the data is not usable anymore. And this was actually an issue during deployment, because we're doing a lot of parallelism, and at some point we were out of sync and everything was fucked. So you should actually take care of keeping everything in sync here. And obviously, if you deploy some work, you should take care of also having an audit of your implementation. Good. Other considerations that you have to take is for performance, to actually get this fast network environment, that the nodes are actually co-hosted in the same data center. So this is to reduce the latency in the network and also increase bandwidth. And this is actually something, if you would put the servers into different data centers, you would really feel that in the performance. So this is kind of necessary here. So further considerations for security is, ideally, we would run these parties in a trusted execution environment. This would increase the resistance I get against the parties trying to collude with the others to get out the real data. It would also increase the resistance of them actually deviating from the protocol. It would also help with further strengthening the security against the data center. But the reason why we don't have trusted execution environments so far is that it's kind of hard to reconcile GPU code and trusted execution environments, but there's a team actually working on that, so we hope we get this done at some point. Then another thing is we also want to have encrypted network traffic between the computing parties, and since we kind of only execute code on the GPUs, it's kind of hard to also get DLS into the network here. So what we do instead here is, since we already have common random number generators between each parties due to using replicated secret sharing at some point, we use these random number generators to create a key stream to encrypt all network data before it leaves the graphic cards. Then I said we have a 3-party protocol, but actually there are 4 partners of World current hosting the nodes, and the reason for that is that we also want to have redundancy there. So whenever an orb is creating a new iris code, it actually creates 4 Shamir shares, sends them out to the 4 parties, but only 3 are used during the computations. And the reason for that is that if one party would be not reachable, or if one party actually loses its database, the whole protocol is still working, up and running, and the reason for that is the 4th party. So that leaves only the orb as a single point of failure, but there's also some security measurements there because the orb has software attestations here, so you can check that it's actually using the correct software. And there's a team also currently working on building zero knowledge proof from creating the picture to creating the secret share, so you can actually check that everything was done correctly. So this brings me to the end of this presentation. I want to conclude with this slide here. First, some learnings. If you want to deploy some MPC protocols, also consider using GPUs. With NVIDIA NCCL, you can really get a huge performance boost out of GPUs, also with MPC code. The second learning is when you have very strong hardware and also protocol optimizations, then you can actually use MPC also for deployments with data of millions of users. So about the protocol itself, there are some future works going on at the moment. So currently, the protocol I mentioned here uses essentially linear scan over the whole database. This, as the name says, scales linearly in the database size. And in the future, we want to have a graph-based solution here as well. So this scales logarithmically in the database size. And there's currently a team from the company Inverse working on that, investigating actually implementing this protocol, what the performance is, and what the leakage actually is. So essentially, when you have a efficient graph-based protocol in MPC, you can leak at every node in the graph, and here you would essentially leak where the new iris code would be in the database. A second future work is there is also consideration of using different authentication services like different credentials like passports, for example. The advantage of using a passport is that you can do exact matching, which is easy in MPC, so a simpler protocol. But the trade-off here is that you don't have biometric authentication, but government-issued authentication. So this is a kind of weaker form of authentication here. But this is also actively investigated. So finally, if you want to have look at more details, the paper is linked here as well. And with that, I want to conclude and thank you for your attention.
Questions? The guy uses eagles. Anybody ask about eagles?
Thank you. Very impressive performance that you get here.
Thanks.
If I understood correctly, the initial database was deleted. Now you have all these 11 million, I think, biometric information that is stored in these 4 shares.
Yes.
So if 2 servers go down, you lose all the database, correct?
Yeah, I mean 3 need to go down, then everything is gone.
3, oh, okay.
Yeah.
Oh, okay, just wanted to know that.
I've heard about backups. No.
Yeah, you mentioned that you deploy actually in the same data center because you also use this NVIDIA Link, which is also kind of designed for that. And for your use case, is that acceptable to actually run those nodes in the same data center? Like, does your client say something about that, or are they fine with it, or is
yeah, I mean, for this use case, it's definitely beneficial to run it there because before that there was no MPC used at all. So the World ID had access to the whole database. So any MPC solution is definitely preferable to that. So ideally, we would have some more strengths in place against, for example, the data center trying to steal the data like the DEs I mentioned. But since with the graphic cards, this is kind of hard, and we didn't, the team working on that didn't achieve that so far. But in any sense, I would say it's definitely better than having one company control all the shares. Yeah.
Let's thank the speaker once more.
Thanks.